In this next section, we're going to get into exponential functions. The first thing that you need to be able to do is recognize the difference between a linear function and an exponential function. So we've got an XY chart that's been written horizontally up on the board here. And we wanted to figure out, is this linear or is this going to be exponential? Remember that with a linear function, every time that you take one step with x, you're going to go the same number of steps with y. So if the first one was you go one right and then you go two up, then the next one's going to be one right and two up, one right and two up. With an exponential function, you're going to have a much steeper slope as you go along. So what's going to happen is, instead of going one step right and then one step up, and then one step right and one step up, what you will do is maybe one step right, one step up, and then one step right, 3 steps up, one step up, 9 steps up. So it's going to be based on exponents rather than based on multiplication. So when we look at this, we can see that we're taking one step to the right every time with x. What are we doing with y? Well, you can look at from here to here as one of two things. You can say that you're subtracting 2, or you could say that you're multiplying by 3. So what we want to do is, in the next step, we want to look at which one of those does it follow. Does it follow the subtracting 2, which would be linear, or is it multiplying by 3, which would be exponential? So to get from -3 to -9, we can subtract by 6, or we can multiply by 3. So right now it's looking as though this is an exponential model. Check it with the very end here. -9 to -27, you're going to multiply by 3. So you can see that since we're multiplying by 3 every single time, we have an exponential function here. For problem 1b, you can see that we're given y equals 3x. Now, if you go back to when we were doing linear functions, you'll remember that the slope-intercept form of a line is y equals mx plus b. So this 3x is just 3x plus 0. So what you can see here is we've got something that's in the form of slope-intercept, and slope-intercept tells us that this is a linear function. For problem number 2, we're given a word problem about the population size of a particular beetle. And we're told that if we start with 30 beetles, what's going to happen is we're going to have a population that follows this exponential model of 30 times 2 to the x, where x is the number of weeks. So what it wants to know is, how many beetles will there be after 56 days? So what we've got to do before we even start working on this problem with the exponential model is convert 56 days into weeks. So we do 56 divided by 7 gives us 8 weeks. So what we're going to do is we're going to plug in 8 for x. So that's going to give us 30 times 2 to the 8th. And then 2 to the 8th is going to give us 256. So if we multiply 30 times 256, we're going to get 7,680. So after 8 weeks, there will be 7,680 beetles. For problem number 3, we're going back to our general or vertex form of an equation. But this time we're looking at it in terms of an exponential model. So we got y equals a times b to the x minus h plus k. Now, the only new thing that you're being introduced to here is the b value. Now, a is still going to be your stretch, compress, reflect. Your h value is still going to represent your horizontal movement, left or right, and your k value is still going to represent your vertical movement, up or down. But now we have a b value, and this is a very important thing to know. B value is going to represent your growth or your decay. So if you have a growth model, what that means is that b is going to be greater than 1. Okay? And then if you have a growth model, then that means that your graph is going to look like this. If you have a b value that is less than 1 but is greater than 0, so it's in between 0 and 1. So let's say a half, 3/4, 5/8, whatever. It's going to represent a decay model. And when it represents a decay model, it's going to look like this. So it's going to be getting smaller as it goes to the right. Growth model is going to be getting bigger as it goes to the right. Now think about if you were putting money into the stock market. You want to see your stocks grow. So what does that mean? It starts out low on the left and ends up high on the right. So if you ever get confused, just remember that you want your stocks to grow. That means that you want them to end high. So when we're looking at our equation here, we've got y equals 3 times 2 to the x. So we're going to go ahead and run through our list of things that we need to answer. A lot of them are already the same things you've already seen, but we do have a couple of new additions to this list. So our a value in this case is going to be 3. So since we have 3, it's greater than 1, we know that we're going to have a stretch. And it's going to be a stretch by a factor of 3. Now our growth or decay, we're going to go to that b value. And in this case, our b value is greater than 1. So that means that we're going to have a growth model. Our h value, there's nothing being added or subtracted to the x. So we get a 0. Let's make sure that shows up. And then there's nothing being added or subtracted to the entire equation. So that is a 0 as well. Now the one thing that you definitely need to know about the starting point of an exponential model, it's not going to start at 0, 0. It's going to start instead at 0, 1. Because if we were to look at the parent function of, say, this function here, y equals 2 to the x, we're not going to have an a value on our example here. If we put 0 in here, well, what's the rule governing an exponent of 0? The solution is always 1. So that means that our starting point, whenever we have a growth or decay model with no a value, that means it's always going to be 0, 1. Now on the one that we've got here, we have an a value of 3. So let's go ahead and run this through. We plug in 0 for x, 2 to the 0th is 1, times 3 is 3. So we get a starting point of 3. So that means we're going to put a value here as our starting point, and we're going to go 0 and then 1, 2, 3. Okay? Now the next thing that you need to know is that all of these exponential models are going to have what we call a horizontal asymptote. An asymptote is going to be a line that our graph cannot cross or touch. Okay? So you can see that what happens with this is it's going to flatten out as it goes on to infinity. And it's going to flatten out right next to that line there. Or this one is going to flatten out right next to that line there. But it's never ever going to cross it, and it's never ever going to touch it. So we need to figure out where's the horizontal asymptote going to be. The horizontal asymptote is going to be your k value. And now since we don't have a k value here, that means that our horizontal asymptote is going to be at y equals 0. So all it is, the horizontal asymptote, remember that anytime you have a horizontal line, it's always y equals a number. In this case, the horizontal asymptote is y equals the k value. So since our k value is 0, we're going to put y equals 0. Our domain, we're going to go back to having all real numbers for our domain, and then our range is going to be restricted by our horizontal asymptote. But this time, the graph cannot touch the horizontal asymptote. So instead of saying y is greater than or equal to 0, we're just going to put y is greater than 0. And so that's going to be our range there. Now we need to find two values less than x and two values greater than x. So let's go back to the old standbys, -2, -1, 1, and 2. Now you've just got to go back and you've got to plug these into the equation and see what you come out with. So you plug in -2. -2, remember that a negative exponent tells you you're going to flip the numerator and the denominator. So we end up with 1 over 2 squared, or 1 over 4, times 3, that gives us 3/4. Plug in -1, you get 1/2. 1/2 times 3 is going to be 3/2. Then you plug in 1. 2 to the first is 2, times 3 is going to be 6. And then you plug in 2. 2 squared is 4, times 3 is 12. And so now you have 5 points, which is enough to graph our exponential line here. So we're going to do -2 and 3/4. So back here, and then go to 3/4. -1 and 3/2, which is 1 1/2. 1 and 6. So 1, 2, 3, 4, 5, 6. And then our last one, 212, is going to be off the graph. So I'm just going to put that up here. And then what you're going to do is, we need to remember that we've got a horizontal asymptote at y equals 0. So I'm going to take out a different color marker here just to show where that horizontal asymptote is at. And then I'm going to graph this so that my graph never ever touches that horizontal asymptote. And then it's going to go up just like that. And it's going to continue off to -infinity without ever touching that horizontal asymptote. Now, this is everything that you've got to go through in order to be able to graph one growth or decay model. Remember, the new things that we've got here are, is it growth or decay? Which means, is it going to continue to grow going up, or is it going to decay as it comes down? And then our starting point, whenever we have just a regular old function, is going to be 0, 1. Our a value is going to have an effect on where that starting point is, as well as the k value and the h value. For problem number 4, we're going to be asked to graph a word problem that has to do with computer mapping software, which allows you to zoom in on a particular place. So the function that's given is f of x equals 100 times 1/4 to the x. So the original problem in the book gave you 0.25. I went ahead and changed this to 1/4 because the fraction is always going to be easier to deal with whenever we're working with these exponents, especially if we ever have to go to a negative exponent. Now, because of the way that this problem is done, we're actually not going to use any negative values. We're only going to use positive values. When we look at our information that we need, we check out the a value. The a value in this case is 100. So this means that we're going to have some serious stretch on our model here. This means that the stretch is going to be by a factor of 100. Then we look at our growth or decay. Do we have a growth or decay model based on our b value? The b value is 1/4, so that tells us that we're going to have a decay model. Our h value is still 0, and our k value is still 0. So we have no horizontal movement, we have no vertical movement. The starting point, though, this is going to be the interesting one, is going to be, if we plug in 0 for x, then 1/4 to the 0th is 1 times 100 is 100. So when x is 0, y is 100. So go ahead and go over here and write that in there. And then we need to, let's just go ahead and call these by tens along the side. So we're going to go there. So this is 10 and this is 100. We're only going to go by ones and two, or we're only going to go by ones along the x-axis, but tens along the y-axis. The horizontal asymptote, again, we're going to look at our k value. The k value is 0, so that means that our horizontal asymptote is at y equals 0. So I'm going to go ahead and put that in on this graph here as well. The domain, we're going to artificially restrict the domain to x is greater than or equal to 0, because for the problem in the book, it doesn't really make any sense to have negative values for your x's. Then the range is going to be, again, we're going to take this horizontal asymptote, y and 0, but it can only be greater than. It cannot be greater than or equal to. So once we've got that done, now we're ready to move on and start plotting some points, or to start creating some points to be plotted. I'm going to go ahead and move this up, and I'm going to take away these kind of brackets that I use here, or these lines that I use in order to show the starting point. So the starting point I'm just going to put up here at the top, and we're going to go 1, 2, 3, and 4. So if we plug in 1, we get 1/4 to the first power is 1/4 times 100. quarter of 25, or a quarter of 100 is 25. Then if we do 1/4 to the second power, we get 1 over 16. So 100 times 1 over 16 is going to be approximately 6 point something. Okay? Then if we put in 3, then we get 1 over 64. So then 100 over 64 is going to be less than 0.5. And then if we do 1 over 4 to the fourth, well, now we're looking at, I believe it's 256. So 100 over 256 is going to be, let's see, I'm sorry, this is going to be just under 2. And then 100 over 256 is going to be right around 2/5. So it's going to be approximately 0.4. So we can go ahead and graph these. We're going to get 0, 100, 1 and 25, so 10, 20, 25, 2 and 6, so right about there, 3 and just less than 2, so right about there, and then 4 and 0.4, so right about there. And then we'll draw the line in that connects these points together, and that will be the graph that gives the solutions to the problem in the book.